thank you all for being here, and I'd like to echo the sentiment expressed earlier, thanking the organizers for organizing this meeting and for giving me the opportunity to speak here. Okay, so I'm going to speak about finitely ramified fields, and most of this is joint work with Sylvia and Franziska. So just to remind ourselves what objects we're talking about, so I'm interested in finitely ramified fields today, and a valued field is finitely ramified. If it is of mixed characteristic, 0p, say, and a certain interval in the value group is finite, so that's the interval from 0 to the value of p. So the value of p might be minimal positive in the value group, in which case this is 1, but it also might not be minimal, might be some finite value. And this E is called the initial ramification index. Good. And really, I would like you all to think of this, at least the characteristic P is somehow fixed. So I'm not interested in uniformity questions, although you can always get them after the fact. And E will always stand for this initial ramification index. Examples, I mean, again, we know them all, but it's just to make sure we're talking about the same thing. So QP with the natural example valuation is surely the archetypal example. Something like QP double brackets T that has a rank 2 valuation. First take the T-adic valuation, then the P-adic valuation. That's also finitely ramified. Certainly finite extensions of these. So P is minimal positive, the value of P is minimal positive in the value group here. These are unramified. If I pass to finite extensions, they might no longer be, but they are still finitely ramified. And lastly, any discretely valued field, or maybe let's put for definiteness, Z-valued field of mixed characteristic that will also be automatically finitely ramified. Good. What's our goal here today? I want to explore the model theory of these guys. Or, well, maybe this is a bit too much. I mean, I want to, as we want to do, explore the model theory of the henselian ones. And just for definiteness, I should fix the language. So I work in the three-sorted language L-val. We've seen it a couple of times this week, so I don't think I need to repeat it. We have a valued field sort, we have a value group sort, we have a residue field sort, and sort of the obvious maps between them in the sense of we have the valuation and we have a residue map that, say, gets continued to 0 outside the valuation. And the expectation of this is that I mean, some of this was very well studied by Ax-Kochen-Ershov in the first papers in the 60s after sort of ACVF, where they developed much of the model theory of valued fields in equicharacteristic 0, but really in concert already with the finitely ramified ones. So one of the first papers of Ax-Kochen, they really give an axiomatization of QP, for instance, which is an example of things that can happen. So just for an example theorem, this is Ershov. Let me check Ershov 67, and independently Martin Ziegler in his PhD thesis in 72 let KV and LW both finitely ramified henselian, then I get as valued fields, these are elementary substructures, if and only if the same thing holds on the group side and holds on the residue field side and on the group side. Okay, and again for definiteness, this is in L-val, this is in the language of rings, and this is in the language of ordered abelian groups. And of course, again, we've seen it a couple of times. This is a prime example of what I want to call an Ax-Kochen-Ershov principle. Behavior on the value group, on the valued field is entirely controlled by residue field and value group. So this is an AKE principle for elementary substructures. And what I now want to do, I mean, we are sort of used to from the theory in equicharacteristic zero, from the theory in tame fields, that these Ax-Kochen-Ershov principles tend to come in a package. You get them for elementary substructures, maybe you get them for elementary equivalents, and perhaps existential equivalents, things like this. And I want to explore how this works here. So first goal, explore complete theories and existential theories of, again, finitely ramified, always in this talk, finitely ramified henselian fields.
In this theorem, they also cover the imperfect present case?
They do. They actually do. I'll have a number of things to say about imperfection and the things in the literature but here it's here they really do. Okay, so I want to explore complete theories first. So Ax-Kochen-Ershov principle for elementary equivalents. And there's, when you look at this for the first time, you immediately see that this sort of needs a fix. So observation. If I look at Q3, a joiner square root of Q3, a joiner square root of 3, Q3, a joiner square root of -3. So I'll be a bit imprecise about the valuation, but it's always the obvious one, so the unique extension of the three-adic valuation. So they have residue fields F3, it's totally ramified over Q3, value group Z, certainly, and they both have ramification index 2. But are not elementary equivalent, namely, well, consider the obvious formula. There exists an x such that x squared is equal to 3. That is true in the left field, not true in the right field. So I guess you need to check that these are not the same fields, but I assure you they are not. Okay, so this means the obvious Ax-Kochen-Ershov principle fails. So I cannot say they're elementary equivalents because their value group and their residue field are elementary equivalent. But I mean, if you've sort of done p-adically closed field, you know there's sort of a finite fix. I mean, you just need to add essentially this formula, and everything will be well. And the same thing works whenever you have a finite extension of a p-adic field. So to the obvious axiomatization, you just add a certain polynomial. One variable polynomial over z has a root. So that doesn't seem too bad. I'll have to make a short digression here before I can resolve what happens in the general case, which is that I need to say a few words about this, the choice of language here. So this is again, I mean, it's either a lemma or an observation. Let's make it an observation. In KV, finitely ramified henselian, I claim that both the valuation ring and the maximal ideal are E definable, and you sort of write down a fairly obvious thing. Let me try to do this. Y to the P equal y to the PE plus 1 is equal to 1 plus P times X to the PE plus 1. Okay, I mean, this is a formula. This is you can check using easy application of Hensel's lemma that OV is just given by this existentially definable set, and there's a similar thing for MV, which I leave as an exercise. So the point is that they are parameter freely, existentially L ring definable. Why do I? So again, this is a standard observation. I mean, Julia Robinson writes this down offhand, so it's not a big deal. But the point is that it allows me to switch my language with impunity. So if I ask you about L-val theories, then I can just use the substitution and an obvious interpretation argument to work in L ring instead. So in other words, the language. I mean, I've said for definiteness I'm working in L-val, but it never matters. So the L ring theory, even the existential L ring theory, completely controls the same thing on the L-val side, and that's really what allows me to be sloppy about valuations in the entire thing. Okay, so we just were this observation over there that the obvious Ax-Kochen-Ershov principle needs a fix. But and then you try to do this, and then it turns out that the fix is not so simple. So I don't really know what this is. This is, I think, let's make this a theorem slash example. And this is, I guess I observed this myself in 22. There's a short note on the archive, which says there exists KV complete Z-valued mixed characteristic 0p such that the theory of the residue field is the existential theory of the residue field is decidable. The existential theory of K is undecidable. And I want to add the algebraic part of this thing, so K intersected Q bar is p-adically closed. Okay, so that's a certain valued field. What is the point of this example? Well, this means that Ax-Kochen-Ershov or existential Ax-Kochen-Ershov fails in a strong way. So if you want to axiomatize this field in the obvious way, you say, well, it's henselian valued, its value group is a Z group, the value of P is whatever it is, the residue field has precisely this existential theory, and you expect the existential theory of K to fall out, but indeed this isn't the case, because on the one side you have a decidable scheme of axioms, but this thing is not decidable, so in particular it's not pinned down by the axioms I've mentioned, and indeed in quite a strong way, because you cannot fix this by adding more decidable schemes of axioms. You cannot fix this by adding. You cannot fix this by adding E1 formulas, because this thing you cannot add a finite amount of data to fix this, because all of this would remain decidable, and it's not. Okay, so. So I guess AKE for existential equivalence fails in a strong way. And I should remark at this point that in equicharacteristic, there's no such example. So even without dropping finitely ramified, just saying henselian, in equicharacteristic we do know that the existential theory of the residue field completely governs the existential theory of the valued field. This is Anscombe theme 16, and indeed they pretty much asked this. So they asked whether there's a counterexample in general without this algebraic condition, without the finitely ramified condition, and then I think Kostas Karatas pointed out that this cannot possibly be true because there's somehow too many algebraic parts. There's already too many algebraic extensions of QP, but somehow this is a valued field that's as nice as possible. I mean, it's complete Z-valued. You don't expect dragons to lurk there. Good. I would like to give an indication of how the proof of this example works, both to discharge my obligation to present a proof, but also because it's actually of some relevance for how we later go about fixing this. Okay, proof sketch. So I take a field, let F. For simplicity, this works in any characteristic, but I'm only doing it in odd characteristic here. Let F be of characteristic P. E over F quadratic extension such that the existential theory of F is decidable and the existential theory of E is not. And my idea is going to be I will construct a valued field with residue field F, so that's existentially decidable, but I'm going to hide this extension E in it, and that is what will witness the undecidability. And in fact, once you've worked this out, this is easy to do. So this is a quadratic extension. So say this is given by F adjoin the square root of alpha, and I'm going to let K naught be complete Z-valued with, sorry, I should give this a name, I guess, value of P minimal positive, and residue field F. So that's a construction of an unramified valued field in mixed characteristic. You can always do this. It's an easy exercise from QP. Let A in K be a lift of alpha, and we set K is K naught adjoin the square root of the element PA, P times A. So A has value 0, certainly it's a unit, lift something in the residue field. So PA is a uniformizer, and this thing is going to be a ramified quadratic extension. So you see K has residue field. Residue field F. But, well, if you adjoin to K a square root of P, then that's the same thing as adjoining to K naught, well, a square root of P and the square root of A this time. So if I join the square root of PA and 1 of P, so I also get a square root of A, has residue field E. This is E undecidable. And so this field is existentially L-val undecidable, But I've already said the existential L-val theory is, for all intents and purposes, the same as the existential ring theory. And thus, K itself is also existentially a ring undecidable because it can interpret everything. Fantastic. You could have been my plant. No, because exactly Ax-Kochen-Ershov, the Arno and Sylvie tell you it cannot work. And some of the point is that you do not have this distinguished element P, which you can. With T in a language, it's a different matter. With T in the language, does this work as well? Yeah, I guess it should. Yeah. So it's somehow that you get one parameter for free is the point here. And Moshe quite rightly asked where you get this thing from, and that's of course the correct question you should ask. So, whence do F and E come? And this is, this is really a construction that should be known, that should be better known. So this is Ershov's theory of fields with a strong local global principle. So I want you to think less Vlere and more Samaria at this point. So Ershof has a very strong theory of fields with a general local global principle for a collection of henselizations of valuations. But you somehow need to be a bit more general about this. So these will be valuations of infinitely many different types. They will have very many different residue fields. And it turns out that in these that these are E-decidable, and you can cook up undecidable quadratic extensions. And I should really mention, this is compare thesis of Kesevan Thanaglpal. I guess this is 2019, so this is an unpublished PhD thesis at Oxford under Jochen Königsmann. And he observed that you can cook up examples like this in characteristic 0. So you can find decidable fields with undecidable quadratic extensions, and somehow you copy this construction, which with a bit more legwork in characteristic P, and you find this. Yeah, it doesn't really matter. I mean, if you perfectify it, you don't change the existential theory at that point. So if you would like to, by all means do. Yeah, sorry. Okay, and I guess I haven't yet told you how to make this the algebraic part p-adically closed, but you just choose the residue field wisely, so it falls out. So the manuscript on the archive in which I note this is called 2 examples concerning existential decidability, because really that's the first and that's the second. So you first need to worry about how to realize this stuff in characteristic P.
Sorry, so perhaps it's just a stupid question, but if I have an equation in E just by writing the real and imaginary part, I can say coordinates in the basis 1 parent of alpha, I reduce it to an equation in...
You can't pin down this element, is the point. Indeed. So with the element, you're dead. You're completely right. But without the element, you can't pin it down. Is the point. Okay. So this means somehow we have. Going back, I said we have a fundamental obstruction to the AKE principle in mixed characteristic here, at least in the naive way. Let me say what the literature has to say on finitely ramified henselian fields, because surely it does have something to say. And here I want to give sort of the perhaps most classical theorem. This is Basarab in 78. Let KV and LW be finitely ramified. Then he tells us they are existentially, they are elementarily equivalent. So full theories now not existential theories, although it doesn't much matter. If and only if, well, obvious condition on the value groups and for all n, these things are elementarily equivalent. So these are known as the higher residue rings. I don't mod out the maximal ideal, I mod out some smaller ideal, namely the one generated by p to the n, and I want these to be L ring equivalent for all n. I mean, you may as well. I mean, it's encoded in there, so you needn't worry. But yes, I mean, if you prefer pointed value groups, you're welcome to. Okay, so this means KV is somehow axiomatized by its value group and the list of all these rings in the ring, the list of all these higher rings in the ring language, and then perhaps much later, answering a question by Basarab, Lee and Lee observed in 2021 that if KV is perfect, it suffices to take one. I don't need this for all n. It suffices to do this for some computable n that depends on p and e. But they only observe this if the residue field is perfect. And indeed, I mean, a lot of the literature is a bit messy in that some things are only stated for perfect residue fields, some things are stated for general residue fields, but the proofs are wrong if the residue field is imperfect. So yeah, it's a bit messy, and part of this project was really to do everything correctly for all residue fields that you can allow. And okay, what do I think of this result? I mean, in a sense, it gives us a complete axiomatization of the full theory. But on the other hand, it's a bit, it's perhaps not as nice as it could be because I've reduced all this complexity to the higher residue field, but they are still not very nice. I mean, I don't really want to worry about higher residue fields. I really want to go down to higher residue rings. I really want to go down to the residue field. And for instance, in bad places, it's not even clear how this thing is interpretable in the residue field, even with parameters. So this can get pretty bad, especially in the imperfect residue field situation. I should mention, for completeness, there are other results. So we know general results for henselian fields of characteristic 0. This is in line with what Raf told us in his talk yesterday, reducing to higher RV sorts. So I guess this was later Basarab and then Kuhlmann and then Flenner in various formulations. But in a sense, higher RV sorts are as bad as higher residue rings, so you don't win anything here. Yeah?
I think there were also results of bicycling in the infinitely ramified case.
Aha, okay.
You know, of the kind that for all n you need to have
okay. Okay, thank you. All right, so that's some of the problem setting, I guess, and why I don't find the literature as satisfactory as it might be. And so now I basically want to show you how we solve this result together with me, together with Sylvia and Francie. Yeah, I'll state this fairly abstractly, I mean, we'll see whether I have time to say anything for how this actually goes. So, results. And again, so if you're interested in this, this has appeared on the archive last week, so you can read up on how this goes. We have a fundamental problem. I've already said the residue field is just not sufficient, so we've got to fix this somehow. And the key idea is we consider residue field in an expansion of the ring language. So I just want to throw in more predicates and hope that this fixes my Ax-Kochen-Ershov principles. Notation. So let fix the ramification index E and consider the theory TPE of finitely ramified henselian fields of given residue characteristic and initial ramification index. And the first thing I want to, and what I now claim is, so there is a constant which I call little m, depends on P and E, such that with the language LP, E, that's going to be ring language plus one predicate omega, so that's a predicate symbol, and this is n adic. That's the expansion of the language I want to consider. Just one, so it's fairly harmless. Add one predicate symbol of arity m, depending on. Oh, sorry, thank you. In array. Clearly can't do language anymore. Good. So I'm just now going to give you a list of properties or a list of things that happen in this expanded language. So for first thing I'm going to say, for a model for finitely ramified henselian field in this regime, the field KV carries an LPE structure, and I should specify this, so there's a formula, certain, so what's this going to be? This is a positive existential L-val formula, phi PE, with some free variables, such that we set omega of k comma v. This is just going to be the interpretation of this thing, and it's a subset of the residue field. So that's the regime I now want to consider. I just endow the residue field with the enrichment given by this particular formula. Okay, there's no results yet as such, I guess. Secondly, for KV and LW, models of, again, Henselian finitely ramified fields with invariance P and E, we get the AKE principles. So they're elementarily equivalent in L val if and only if the residue fields are equivalent and the value groups are equivalent. And to make this not a contradiction with what I said before, I need to, of course, enrich the language. So this says replacing L ring by LPE fixes this defect. And the same thing happens existentially. Sorry? Indeed, it's completely uniform, this being the point. And to make this true, I have to put here not existential, but positive existential.
This is a particular formula.
Yeah, it's explicit. I mean, it's. I'll say a couple of words. I'll say a couple of words later. And I've dropped the value group, but this is, as always, because all value groups are existentially equivalent anyway. So I don't have to put the value group.
Once again, you don't need the constant in the value group because somehow.
Well, I've already fixed E. So saying so there's no statement. Yeah, so I mean, I guess if whether I put existential here or positive existential here doesn't matter, in the sense that I guess I've already said you could use the language of rings instead, and in the language of rings, existential and positive existential is the same because I can eliminate inequalities. So if you prefer things to be symmetric, you're welcome to put a plus here. And the corollary is, I guess, where the transfer of decidability. So yeah, clearly if both of these guys are decidable, then this is decidable, and the same thing on the other side. To satisfy Moshe, I should explain how this works in a particular case. So and the first example I guess you should look at is E equals 1. In the unramified case, so P is minimal positive, everything works. So in the unramified case, all the difficulties disappear anyway, everything works in the language of rings, and I guess I should point in the direction of Anscombe-Jahnke 22. So if P is minimal positive, then this is the case that most people worked on. Again, there are some mistakes in imperfect residue fields, and you should just read Sylvia and Francie's paper for the details and the history of all of this. And for us, so what sort of falls out of our proof when you do this? Well, what happens is that M of P and 1 is just 0, so omega is a zero array, a null array relation symbol, and our formula is just Virums. So I mean everything just trivializes as it ought to. And now I want to look at the case of P odd and E equals 2. And I guess I want to look at this because this is the regime that we were in our proof above there. We had odd P and an extension of and a quadratic extension. And there what happens is that we can take M equals 1, so this works with a unary predicate now instead of a nullary predicate, and phi P of 2 of x expresses there is a lift A of x such that x squared minus PA has a root. Okay, so this is an existential L-val, a positive existential L-val formula that asserts something about the residue X. And I claim this makes all of this true, and I guess I'm going to go to that board. So what happens if you interpret it over there? Well, sort of by construction, alpha certainly satisfies this thing because that's exactly how I constructed things. And indeed, the entire square class of alpha satisfies this thing. So in the proof of the theorem / example, the omega predicate of KV is just, or let me perhaps put it like this, the L-val structure KV is just the field F together with the square class of alpha. So my predicate omega is precisely the square class. And indeed, this explains the undecidability because once you know the square class, it exactly happens what Antoine asked earlier. Once you know the square class, you know E, and E is undecidable. So that's why this thing is undecidable. And this fixes this. And indeed, similar idea works whenever P does not equal E. So this is the case of tame ramification. So that's why P odd E equals 2 was the relevant regime here. In tame ramification, you can always take a unary predicate, something similar like that. And in a sense, it's the baby case. So really, the wild ramification is the more difficult one. Good. Okay, so that explains what's going on in this regime. And now I think, perhaps I have one more board here. So at the moment, I mean, I haven't showed all my cards yet, namely what's going on with this phi in the wild case, but I guess I should convince you that somehow this is that's not too bad. And I guess I might call this something like naturality. In fact, this is a generalization of one of these Ax-Kochen-Ershov principles. So every positively existentially parameter freely positively existentially L-val definable subset of KV is in fact so every subset of the residue field I can define in the residue fields positively existentially, I can already define knowing only the LPE structure. So the point being somehow that the positive existential structure induced by this predicate is very natural. It is the right structure. And in fact, this whole thing is uniform in models of my theory. So I'm asserting for every positive existential L-val formula, there exists one positive existential LPE formula which works in every model. And why is this good? Well, if you think about this for a moment, this thing already characterizes omega up to positive existential by definability. So I haven't pinned down omega and phi completely yet, but I've pinned it down up to positive existential by definability, interdefinability, which is already pretty good, I think. Yeah, I should mention. So if you ask this thing for sentences, then you actually get the AKE principle out. So this is a generalization of the existential AKE principle. Right. No. I guess at that point, I sort of might as well I mean, now looks like this construction does what I wanted from it initially, and it's also fairly natural. And now I should, I guess, write down some other nice model theoretic things that follow from the construction. And I also want to compare to the results by Basarab, which I'm just erasing. So, for model theoretic bonus, sorry, I guess I should said something about existentially definable things here. I might as well say something about full things. So, every parameter-free L1 formula, well, phi is already taken, let's name it psi, with two tuples of variables where I want this to be in the value group sort and I want this to be in the residue field sort, is equivalent in the theory to a Boolean combination of ordered abelian group formulas and residue field formulas in the enriched language. So the point being that as far as parameter freely definable sets are concerned, these sorts don't talk to each other, and the things that are definable are exactly the right ones. So this is again another example that these things talk to each other, are the right things. In particular, LPE is precisely the induced structure. So the traces of zero definable sets are precisely the LPE definable ones. Again, this is good. Secondly, and I guess I should have prepared something clever with colored chalk, but I didn't. So let me write this out again for a model, every every formula now allowing parameters from this one model KV is equivalent in the model, or I guess what is the same modulo its elementary diagram, to a Boolean combination of well, value group formulas now allowing parameters and residue field formulas. So it's more or less the same thing as over here, but allowing parameters working in the specific model. And through some fluke of fate, I even get L ring here instead of LPE. Okay, that's a bit funny, but that's just how it works out. And I guess it comes from the predicate even being definable in the residue field, but with parameters only. So somehow the parameters save your bacon. And I guess a different way of saying this is that the two sorts are stably embedded and orthogonal, and the structure is exactly the right one. So purely SE and orthogonal. Good. Okay. So that's the that's what this gets out. Fifth, I promised some comparison with the Basarab and Li results. So, and it turns out omega only depends on a higher residue ring, namely for sufficiently high n, you can recover the omega from a sufficiently high residue ring, and definably, so the formula just only looks at this in the first place. It's very obvious. I'm not claiming the n is the same as that obtained in Li, but it's certainly related. I haven't actually checked whether it's the same. So in particular, but we don't have this restriction on the perfect residue field. So it just flat out works out for all residue fields, which is quite nice. Good. Then let me. So these are the 5 nice things about our construction. I should also hint at less nice things. And the first one is, all of this package that I mentioned here normally follows from quantifier elimination. You get all your stable embeddedness, your nice induced structure, but we don't have quantifier elimination down to Vk and Kv. I guess that's too much to ask for, but we don't even have this even with a cross-section. So even if you add all of the nice things, cross-section, structure on the residue field, you don't get quantifier elimination, and indeed, to be precise, one cannot eliminate a p-th power predicate. So that's something you cannot eliminate. You can try writing this down, and somehow what seems to play a role is we know all of this for QP, that you can that things fall out nicely, and somehow it seems to play a role that the residue field is perfect, but really also all subfields are perfect, and that already gets you down to finite residue fields. So something fundamental here is not working, and I think things would become much more complicated if you wanted to find a language in which you have quantifier elimination. And the second less nice thing is that I gave you this example of the tamely ramified situation where you can take m equals 1, but in general, really, this function grows very fast. So we're really talking sort of a tower of powers of p. In E. It's primitive recursive, but really nothing much better than this. And really the cause for this seems to be that we handle imperfect residue fields. So if you were in the perfect situation, then it's some sort of it grows no worse than e to the 3 or something. So it's a very tame polynomial that you get in this regard. But allowing imperfect residue field really makes this blow up very badly. If E is fixed, it still grows, yes. You can, it just depends on P. Yeah, I mean, it's one of the first things we do in our paper to write down. Well, I mean, we present the set it defines. We don't, write it down with all the brackets and details, but we give it explicitly. We explicitly write it down.
So for fixed E, the number of exponential, the stack is down.
Yeah, that's how it works out. And well, I guess I have about 2 minutes to say something about the proof very quickly. So I guess, you'll have to look in the paper, obviously, because I can't say everything here. You reduce very quickly to understanding complete discretely valued fields. Somehow everything else you do with the equicharacteristic 0-0 machinery, that's harmless. So we really need to understand the complete rank 1 situation. And there you somehow use all the machinery. You use the machinery on unramified fields as presented in Anscombe-Janke, and then you somehow try to present a general ring by saying it's an extension of an unramified one by some minimal polynomial, which is Eisenstein, and then you try to, but you only need to know this minimal polynomial up to some, you can wiggle it a bit by Krasner's lemma, it doesn't change the situation, so you need to know this minimal polynomial up to some finite precision, and that's exactly what the omega encodes. So you encode this minimal polynomial, and then somehow you get an embedding lemma for complete z-valued fields, and then everything else falls out through standard machinery. Okay, thank you.
Okay, thank you so much. Questions?
So can one interpret the Basarab sorts, like the higher residue rings, can they be interpreted in the residue field with this predicate, or does something go wrong?
I haven't... okay, let me say the first thing. So if you restrict to perfect residue fields, then everything is somehow fine, because in the unramified situation you are done a truncated Wittring, and you just sort of formally adjoin a root of your polynomial, and then everything is nice enough. But especially if you have a higher residue ring, especially in positive character, say infinite imperfection degree, then somehow you still get a Wittring, but that's somehow a very small part of your valuation ring. So it's not. If you do this in a natural way, then you're no longer finite over this Wittring. You're still integral, and then I, at the very least, don't know how to do it, and there seems to be no natural way of doing this.
So, are these residue rings, they're always sort of internal over the residue field, right? This is maybe fibered by finitely many steps in each.
That's in the perfect case.
Oh, that only works for the.
Yeah, I think this is only for the perfect case. Right?
Wouldn't you just take each of these things has a map to the previous one, and the fibers are all the residue field?
No, this is the perfect case.
Okay. Well, anyway, yeah, I guess it seemed like these structures seem very close to the residue field in some very weak sense, and maybe this predicate phi PE is determining these things up to isomorph, or maybe at least up to elementary equivalence.
It obviously does.
Yeah. So it's definitely determining them up to elementary equivalence. Does it determine them up to isomorphism?
Yes, I guess it. It must after the fact. Somehow the embedding lemma then tells you that it does determine them actually up to isomorphism.
Because then it starts to feel like by some formal nonsense they ought to be sort of, I don't know, interpretable. Or
they're very close to being interpretable.
Or some kind of cover.
It's related. It's somehow related to, I guess, knowing an algebraically closed field given a field. It's.
Oh yeah.
More questions? Okay, so let's thank Philippe again.